Power output. An external resistor with resistance capital R is connected to a battery that has EMF epsilon and internal resistance R. Let P be the electrical power output of the source. By conservation of energy, P is equal to the power consumed by capital R. What is the value of P in the limit that R is very small and very large? Show that the power output of the battery is a maximum when capital R is equal to R, the internal resistance, and what is this maximum power P in terms of epsilon and R? And finally, give it some numerical values. A battery has epsilon equals 64 volts and internal resistance 4 ohms. What is the power output of this battery when it is connected to a resistor capital R for capital R equals 2 ohms, 4 ohms, and 6 ohms? Are your results consistent with the general result you derived in part C? So here is our battery internal resistance R, EMF epsilon connected to this resistor R. The current flows from top to bottom. The current I call I. Now, because these two resistances are connected in series, I can write that the current is equal to the EMF epsilon divided by the equivalent resistance capital R plus R. What is the output power of this source? It's going to be equal to the power consumed by the resistor I square R, which is, for I can substitute epsilon over the equivalent resistance. So this power is epsilon square capital R divided by capital R plus R squared. Okay, now part A. What is this output power in the limit R goes to 0? In the limit capital R becomes 0, there will be no power dissipation. So the output power will be, if you substitute here R equals 0, the output power will be 0 watts. Part B, what is it in the limit capital R goes to infinity? In the limit capital R goes to infinity, because I have the limit capital R goes to infinity, epsilon square capital R divided by R square here, because capital R will be much greater than R, so this will be neglected. It's going to be 1 over R dependence, which is also going to give me no power, 0 watts. Okay, so if the output resistance is 0, then it's going to be no power output, and also when it is infinite there will be no power output. So there has to be a maximum power output somewhere, which is the part C. Part C is asking me, when is this output power 0? If I take the output power derivative with respect to variations in the resistance R and set it equal to 0, I can find its extremum point. So the derivative of this function with respect to capital R, first is going to be the derivative of the top, which is epsilon squared multiplied by the bottom, capital R plus R squared, minus derivative of the bottom, derivative of this, 2 capital R plus R multiplied by the top, epsilon squared capital R, divided by the bottom squared, capital R plus R to the 4th power, and this is to be set equal to 0. So you can see that epsilon squares will cancel. I will be left with capital R plus R parentheses squared is equal to 2 capital R plus R times capital R. So capital R plus R is not equal to 0, so I can cancel these two. And I will find that capital R plus R is equal to 2R, which means the extremum point occurs when capital R is equal to the internal resistance of the battery R. What is this maximum power? P out maximum. It's going to be, now I set capital R is equal to R, which means it's going to be epsilon square R divided by 4R squared, because it's going to be 2R here. And that will give me, for the maximum output power, epsilon square divided by 4R. All right. Now let's plug in some numbers for part D. What is the output power when R is equal to 2 ohms? When capital R is equal to 2 ohms, I have, for a 64 volt source, epsilon square, 64 square times capital R times 2 divided by capital R plus R, R is 4 ohms, squared. This gives me 228 watts. What is the output power when capital R is equal to 4 ohms? That is the internal resistance of the battery, which is 64 square times 4 divided by 4 plus 4 squared. Indeed, this number is 256 watts, greater than the number for 2 ohms. And what is the output power for capital R is equal to 6 ohms? It's going to be 64 squared multiplied by 6 divided by 6 plus 4 squared, which is 246 watts, indeed less than the power for R is equal to 4 ohms. So this result is consistent with part C, indicating that the maximum occurs when the load resistance is equal to the internal resistance of the battery. So here we have a battery with EMF epsilon, internal resistance R. The current through this circuit is epsilon divided by R plus capital R, because the equivalent resistance for the series connection of R and capital R is capital R plus R. The output power of this battery is equal to the power dissipated by capital R by conservation of energy, which is I square capital R. So I obtain output power as a function of capital R. In the limit R equals to 0, this is 0 watts. In the limit R goes to infinity, because of this 1 over R dependence, R over R square, it's also 0 watts. So I start from 0 and at 0. There has to be a maximum somewhere. If I take the derivative of the output power with respect to resistance, set it equal to 0, I see that the extremum point occurs at capital R is equal to the internal resistance of the battery. When I substitute this value to the output power, I see that it is positive, which is epsilon square over 4R. Indeed, this is a maximum value. And by substituting different possible scenarios for the output resistance, 2 ohms, 4 ohms, 6 ohms, for a circuit that has internal resistance, a battery that has internal resistance 4 ohms and epsilon 64 volts, I find that the answer is consistent with part C. Indeed, the maximum power, output power, occurs when the output resistance 4 ohms is equal to, or the load resistance is equal to the internal resistance 4 ohms of the battery.